Hello, Chemistry 11. This is Mr. Chan, and today we're just continuing on with this lesson on the wave mechanical model. Now, last day, hopefully you folks had practice in terms of how do you write the electron configuration for specific atoms. And hopefully you did get a chance to use the orbital diagram and sort of practice writing out the electron configurations. Now, one thing you will notice is that you get a little kind of tedious, especially with some of the elements with more electrons. It seems to go fairly long in terms of the electron configuration. Sometimes you can get to the 3, 4, or 5th energy levels. So there is a way to sort of shorten what we write. So in this case, we need to go back. It says with this new model, when we say valence electrons, it only includes the electrons in an atom except those in the core notation. Now, what is a core notation? Is basically in electrons in completely filled s and p orbitals of the same energy level, generally a noble gas, or in completely filled d or f subshells. And when we talk about valence electrons of nonmetals, they rarely exceed 8. Now, let me give you an example of what I mean. So let's say we did one here, sulfur. Okay, we had 16 electrons. So if I were to write sulfur, it would be 1s2, 2s2, 2p6, 3s2, 3p4. Now, this right here, up until this point, this would be considered the core notation. Because notice, the s and p orbital of the same energy level, in this case, the second energy level, is completely full. So that's the core notation. And the remainder here, this would be considered my valence. And in this case, there are 6 electrons. Okay. Now, in this particular case, if you take a look at the core notation, notice it is 1s2, 2s2, 2p6. And in this case, this is the configuration for neon. So another way to write sulfur would be brackets neon, and then 3s2, 3p4. So what you want to do is look for the nearest noble gas. In this case, to sulfur, it is neon. Okay, so here, if you want to see if I have my periodic table here. So here, we have sulfur. The nearest noble gas that it just passed is neon, because it hasn't reached argon yet. So what you could do is you could do square brackets, and then you could go 3s2, whoopsie, and then 3p4. Another example would be something like calcium. So if you had calcium, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. This would be the core notation. And which element has this exact electron configuration would be argon. So you could write it as argon 4s2. Okay. So you could say, oh, instead of writing that entire 1s2, 2s2, so on, I do argon. And why is it 4s2? Is because calcium is in the 1, 2, 3, 4th period. So that's where we have it here. And then it goes 1, 2, and that's why it's S2. Okay. Now, I said also in completely filled D or F subshells. So let's give you an example of chromium. So in chromium, if I draw a line here, chromium, recall, it has 1s2, 2s2, 2p6, 3s2, 3p6, 3d, was it 4? And 4s2. Notice the 3d is not filled. So what would be the number of valence electrons? Is I would take this. And so what I would have is I would have 6 valence electrons. Now, what would we mean by D completely filled? Is what you're looking for is for D completely filled, you would be looking for D10 or F, I believe, 14. Those are what we call completely filled. Okay. In this case for chromium, the D was not completely filled. That's why we have 6 valence electrons. Now, when writing electron configuration for ions, what we've done is we have focused solely on neutral atoms. For negative ions, very straightforward. We add electrons to the last unfilled subshell, starting where the neutral atom left off. So let me give you an example here. So let's say we have chlorine. So chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. If I had chlorine minus 1, I would just add one more. 2s2, 2p6, 3s2, 3p6. Notice I added one more. So if I do here and here, look. Now, what if I added one more chlorine? So, or sorry, one more electron. So let's say chlorine minus 2. I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now, you might say, Mr. Chan, why did you need to do 4s1? Why can't you put 3p7? Because remember, 4p, the p orbital here is maxed out. Max at 6 electrons. So I had to add one more. Okay. Now, for positive ions, electrons in the outermost shell, keyword is outermost shell, or the highest energy level, are removed first. And if there are electrons in both the s and p orbital of the outermost shell, then the electrons in the p orbital are removed first. What do I mean by this? So let's say, for example, we take aluminum. So we have 1s2, 2s2, 2p6, 3s2, 3p1. Now, if we did aluminum +1 or +1, notice we take the electron away from the 3p orbital because we have an s and a p. We take it away from this one first. So in this case, it would be 1s2, 2s2, 2p6, 3s2. Okay, so notice what happened here. I took it away from the p orbital because they're both in the third energy level. Now, what do I mean by outermost shell? Let me give you an example. Let's say we did, let's say we had chromium. So if we did chromium, normally it would be 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s. Again, what you want to do is you want to look for the highest energy level. So in this case, the 4s2 is the highest level. So if we had chromium +1, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s1. Okay. Now, when an element and an ion have the same electron configuration, they are said to be isoelectronic. Now, for example, let's say we have oxygen -2 versus neon. Now, if we did oxygen -2, it'd be 1s2, 2s2, 2p6. Neon would be 1s2, 2s2, 2p6. This is isoelectronic. Because they both have the same configuration. Now, some of you might say, oh, Mr. Chan, all I need to do is look at the number of electrons. Yeah? The answer is no. For example, let's say we had calcium versus scandium. Scandium +1. Now, for calcium, it would be 1s2, 2s2, we've done this, 2p6, 3s2, 3p6, 4s2. Now, for scandium +1, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, 4s1. If you count, they have the same number of electrons, but this is not isoelectronic. Because they do not have the same electron configuration. Okay. Now, remember, when we talked about charges back in chemical naming, the combining capacity is the number of electrons an element gains or loses to get a full S&P orbital in the outermost shell. Now, what do I mean by this? So again, why notice oxygen has a charge of -2. If we write the electron configuration, it is 1s2, 2s2, 2p6. Notice the S and P are full. If we did something like magnesium plus 2, magnesium plus 2 is 1s2, 2s2, 2p6. Again, also full. So this is why atoms either lose or gain electrons, because it's theorized that they want to get the full S and P orbitals in their outermost shell. Now, how does that, again, a reminder, how does that relate back to the Bohr model? Is because if you take a look at the number of electrons in the S and P orbital, what you have is you have 8 electrons. And finally, elements in the same family have the same number of electrons in their valence shell. For example, if we took lithium, sodium, and potassium, and what we did was we wrote out the electron configurations. It'd be 1s2, 2s1, 1s2, 2s2, 2p6, 3s1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Notice the last shell have 1 electrons in their s orbital. So this is why they are in the same family. Because they have the same number of electrons in their valence shell. All right, folks, that covers the electron configurations. Thank you very much. Have a good day. Bye-bye.